Institute of Engineering and Technology.
Hello students, today we are going to focus on a last part of our infinite series. This part is in fact the most useful part at the beginner level of approximation of a function in form of series. As I promised you that at the end of this infinite series you will get idea that why we are so much concerned about series representation of the function. So this is the time where we are discussing our first approximation of function with help of a series which is in fact infinite series. Today we are going to discuss series representation of any random function with help of different ordered polynomials. And this part is known as Taylor's series expansion of any function. We'll see it in two different categories. We'll divide this talk into two parts, as first part is concerned with Taylor series of the function, as the second part is concerned with the Maclaurin series of the function. Maclaurin series is in fact a special case of Taylor series. Whenever we have a convergent series, in our last talk we have gone through this part which is known as interval of convergence, or you can say radius of convergence, and how we can deal with this radius of convergence. Once we have this idea that our series is convergent in some interval I, we can select a point A from that interval and we can find its series expansion with help of this topic of discussion which we are going to consider in detail, which is Taylor series. Now, if your interval of convergence is in such a way that it contains the origin inside it, then if we expand our series about point origin, then it is known as Maclaurin series. So, Maclaurin series is nothing but a special case of Taylor series where we are taking a point of our expansion or a center of power series as an origin. So I hope this will help you to find any function's polynomial representation in such a way that it contains infinitely many terms. Our next discussion after this would be a trigonometric expansion, which is nothing but Fourier series. So without wasting much time, let us start our first part, which is infinite series, and as I told you, it is Taylor series. Focusing first of all on this topic Taylor series, let us check what is its actual formation. So let f be a function with all derivative in interval I, which contains our point x equal to a, then the Taylor series which is generated by this function f about point x equal to a is defined by this infinite series. Now if you look carefully, this is nothing but a power series summation n from 0 to infinity a n x minus a raised to n. But here the coefficient a n is replaced by a particular value which is f raised to n at a upon n factorial. Remember this f raised to n, f superscript n indicates the nth order derivative of the function which is considered at point A. So remember, this is nothing but your definition of Taylor series of any function at any point x equal to a. Now let us consider one more formation of this. Suppose I shift my value from x to x plus h, then this is how you can find the value of Taylor series with help of this shift h. So if you notice carefully here, I am replacing x minus a by h, so that means the difference is now value h. So it will make comparatively more clear that how you can replace the value of this difference x minus a with h also. In certain cases our first formation is useful, but there are some cases in which we will see our second formation also. So let us go for the another part of this Taylor series, which is known as Taylor's polynomial. What do we mean by polynomial? Whenever we are saying that a polynomial of order n, that means it is a polynomial with the highest degree term n. So now let us check, as we are dealing with the infinite series with the different powers of term x minus a, how we can consider that infinite series with a finitely many terms, and what do we call it, or what do we mean by that special case of Taylor series. So if f is a function with all possible derivatives starting from 1, 2 up to capital N within some interval I which containing a point x equal to a, if I want to find a Taylor's polynomial of order capital N at point x equal to a, I should take first n terms only of our Taylor's series, and this will give you a polynomial representation of your function, which is nothing but f of x. So this part is known as Taylor's polynomial of order n for any function small f at point x equal to a. Now let us move to its graphical representation. For example, if I take f of x as sin x, and if I expand it through Taylor series, then ultimately by taking n equal to 1, 2, 3, 4, it will give you this kind of approximation. So as much as the value of n is concerned, it gives you the best approximation if you increase the value of n. If you look carefully, n equal to 1 was a straight line, then n equal to 2, 3, 4, 5. Slowly they are nothing but the embedment of this new graph on our sine curve. More the value of n, more the accurate approximation of our sine curve. So why these polynomials are useful? If you want to approximate your function in a certain range, for example say minus 5 to 5, you need to take only n equal to 7. No need to go for the further expansion, no need to find all further derivatives. So this is how you can consider your values for given function with help of Taylor series, and the benefit is that it represents your function in form of a simple polynomial, which is very useful in case of derivative, which is very useful in case of integration also. It may happen you are dealing with the complicated function, and if you want to find its derivative and integration, it may happen we don't know, or we don't have any analytical method or the direct method to find its properties. But once you represent it in terms of Taylor series, it will be very easy for you to convert it in form of polynomial and then to find all the properties like derivative, integration, or you can do further mathematical analysis also. Now I want to give you one form example that how actually we can find all these terms for the function and how we can represent it in form of Taylor series. So for example, if I take my function 1 by x and if I want to center that point at a equal to 2, so this gives me that I want to expand this function 1 upon x and my center of expansion should be a equal to 2. So for that, let me consider first of all the function which is 1 by x. As we know that we need to find all possible derivatives of this. So I am taking f dash, which is minus 1 by x square, f double dash minus 1 whole square into 2 factorial upon x cube, and then if I generalize it, it finally gives me f raised to n as minus 1 raised to n factorial upon x raised to n plus 1. Now if I take my value a equal to 2, I need to replace this value of x. Then it gives me corresponding values of f dash or f raised to n at point 2. Now let me take all these inputs in my Taylor's series. So if I take all these inputs in my Taylor series, ultimately it will result into 1 by x as 1 by 2 plus minus 1 raised to 1 by 2 square x minus 2 plus minus 1 whole square into 1 upon 2 cube x minus 2 whole square, and so on up to minus 1 raised to n upon 2 raised to n plus 1 into x minus 2 whole raised to n. So this is nothing but my Taylor's expansion of 1 over x at point equal to 2. Now if you look carefully, if I change the value of a, the value of coefficients and the term x minus a is changing. That means overall calculation will remain almost the same, just I am taking different input for the calculation. So the first line f raised to n x, it remains as it is. The only thing which is changing in all possible expansions of this function 1 by x is the center of expansion, which is value 8. Now let us consider what actually we are finding graphically by adding all such terms into the series. So my first thing is I am representing my original function 1 over x. Now what will happen if I take my first value only? That means I am taking Taylor's polynomial with n equal to 1, only one point at a time. So it gives me 1 by 2. And so if you look carefully, it gives you only a straight line at height plus 1 by 2 and which is parallel to x-axis. Now slowly I am increasing value of n. So this is nothing but n equal to 2. If I take n equal to 2, it is 1 by 8 x minus 2 whole square. So if you look carefully, it gives you a small part of the parabola which is represented by this x minus 2 whole square. Actually it looks like a straight line, but it is not a straight line. It is a part of a parabola which is with a very small curvature. And then slowly if I add more terms, if you look carefully, this orange graph is with n equal to 3 and it gives you a fluctuation which is again very much close to the function. So more the values of n, here I am taking n equal to 4. So there are 4 terms into the count and you can see clearly that it is almost on that our first function 1 over x in surrounding of that point a equal to 2. So if you look carefully, here I am taking a center a equal to 2. So all these polynomials will intersect each other at this point a equal to 2. And so ultimately if you look carefully at the first point, it was touching only at the graph. Slowly we are adding the curvature in the graph and we want to find a perfect embedment of our new polynomial representation of the function which can cover your whole function. This is whole idea about Taylor series. How we can consider this part in such a way that it will give you the full access to the function in a certain interval but with help of a polynomial. So in this graphic you can see clearly I am adding all the properties of Taylor series up to n equal to 4. So step by step we are moving towards that red graph. It is a straight line, a parabola with a very small curvature, a cubic graph and then a quadratic graph. This is how we are moving towards the function using polynomial approximation. And then if you look carefully, as I told you that all these values are intersecting at point x equal to 2 and this means that we are taking expansion at center a equal to 2. So this is whole structure of Taylor's representation of function 1 by x at point a equal to 2. I hope by these two graphics you can see very clearly that what do I mean by term addition into Taylor's polynomial. And then if you look carefully, if you take infinitely many terms, so what will happen ultimately? It will represent your graph on real line R. Now let us move to the extension of Taylor series, which is Taylor series for f of xy. This simply means that now we are taking two-dimensional input and then we want to find its Taylor's series. So if I take a function which is with the continuous partial derivatives of all orders within some interval I, now here interval simply means that an open disk which contains our point of center which is AB. Then the Taylor series generated by this function at point AB is given by this notation. We will not go into this part that how actually it is derived, but here if you look carefully, our first coefficient is f dash and here it is represented by h f of x plus k f of y, and that means we are taking all possible combinations of the partial derivative of order 1. Similarly in the second term I am taking all possible terms of second order partial derivative which is at point AB, and this gives you a Taylor series expansion of the function at point AB. Now let us move to the second part Maclaurin series. As I told you earlier also, Maclaurin series is nothing but a special case of Taylor series where we are focusing on origin as a center of expansion. So the definition is something like this, that if f is a derivative, if f is a differentiable function with all possible orders and within interval I, if it contains the point which is origin, then its Maclaurin series is given by this. I am simply replacing my value of a with 0. Nothing more than that. Now let us move towards its example. So if I want to find Maclaurin series of this function cos x, see, finding Maclaurin series simply means that you want to approximate this function cos x with help of the polynomial's expansion. So again, my regular process is to find all possible derivatives. I am taking f, f dash, f double dash and so on, and then at point x equal to a, I am finding the values. So the Maclaurin series is nothing but a Taylor series at input a equal to 0. So if I fix this formation and if I take all these inputs in the series, then it gives me that cos x is nothing but 1 minus x square plus x raised to 4 minus and so on. This representation you are using almost everywhere whenever you have function cos x. So this is the fundamental process to find representation of cos function in form of series. It is known as Maclaurin series. Similarly, you can find Maclaurin series for all standard functions like log of 1 plus x, e raised to x, sin x and so on. Now let us check graphically what actually it is happening. Now here again I am taking term by term addition of Fourier series, and that means I am considering all I am taking term by term addition of Taylor series, and so I am taking term by term n equal to 1, n equal to 2 by Taylor's polynomial. So if I take n equal to 1, it was a straight line. If I take n equal to 2, it is a parabola. So if you look carefully term by term, I am molding my graph in such a way that in that neighborhood of point x equal to a, it just covers the whole graph, which is nothing but cos x. So finally, whenever I will take that fourth approximation, although n equal to 4, it gives me that in neighborhood of point 0, now we are almost done. We can take this approximation whenever we are very much closer to this point origin. So this is term by term evolution of infinite series, or you can say a Taylor series with n equal to 4, which is a special case known as Taylor's polynomial. So I hope all of you are now pretty much clear about this idea of series expansion of the function in form of polynomial known as Taylor series and Maclaurin series. Our next talk would be on how to do such expansion with help of circles, which means with help of sine and cos, and that will be very interesting talk where we are discussing Fourier series. We'll see Fourier series in detail, where actually the difference only is now we are approximating function with help of circles. Remember, in Taylor series we did that with help of polynomials. Thank you.
LJ Institute of Engineering and Technology.